Stanford University.
Welcome. Welcome to EE380. We're approaching the end of February, the end of the quarter, and all that other cool stuff. I didn't know that Charles Darwin and Abraham Lincoln were born on the same day 200 years ago. Sort of an odd coincidence. But it's not actually all that much of a coincidence that today's speaker is somewhat related to Charles Darwin's observations of the world. If I recall correctly, the title Engines of Creation was grabbed by the nanotechnology people. Today's speaker is at the forefront of using computers to make a somewhat related engine, engines of invention, which is sort of magic. Picasso claimed that computers were uninteresting because they just gave you answers, but look at the sort of answers we can now get. And Stanford, we've all done the bit of AI of, what can computers do, what can't computers do, and wherever you drew your line, somewhere in their creativity probably was on the not doable side. Today's speaker sort of shatters that. Like most bits of magic, the pieces don't look all that interesting by themselves, but the result of putting them together is surprising. That's what makes it magic. Like most of our speakers, of course, Dr. Koza has done a lot of cool things, but I think he's the first one that I could, in memory, who constructed a tax on the mathematically unsophisticated, aka the scratcher. Dr. Koza.
Well, thank you very much, and I want to thank the organizers for inviting me here today to EE380 to discuss a Darwinian invention and problem solving using a technique called genetic programming. This is, within days, the 200th anniversary of Darwin's birth, and this is a technique that's firmly footed in Darwin's work. So I'll have an introduction. I'm going to describe this technique, genetic programming. Then I'm going to describe a developmental version of genetic programming, which is very useful when you're automating the design of complex structures like analog electrical circuits or antenna or optical lens systems or controllers or metabolic pathways or any number of mechanical systems, quantum computer parts, or any number of other complex structures. And I'm going to show you some results that we consider are not only human competitive, but routinely produced. And then, since this work has now been done in a variety of different domains, from analog electrical circuits to controllers to antennas to quantum computer circuits and mechanical systems, I'm going to try to make some cross-domain observations which are possible now looking back over the last few years as this stuff has developed. We'll talk about parallel computing, which is the mother's milk of genetic programming and the key to making this work, and try to link up the different years in which different results have been produced with the progression of Moore's law. And then we'll talk about what might be done in the future and give you some clues as to where to get more information. One of the quotes I like the best from Darwin's 1859 book on the origin of the species is this quote where he observes that if variations are useful to any organic thing occur, then assuredly individuals thus characterized will have the best chance of being preserved in the struggle for life. And then, because of the principle of inheritance, they will tend to produce offspring that are similarly characterized. And this is the principle that Darwin named as the process of natural selection. Now you have natural selection in organic living things because of four factors. First, they reproduce themselves precisely because they are living, reproducing things. And secondly, there's a population of entities that are reproducing themselves. And these different entities have variations in structure, whether that's innate or caused by simply the imperfection of the reproduction process, or in some cases due to explicit genetic operators which intentionally and purposely create variation. But there is variation. And then if the fourth element exists, that is, if the variation has some effect on fitness, that is, the ability of the individual entity to grow to the age of reproduction and reproduce, or affects the fecundity of the reproduction, that is, how many offspring, if that fourth condition, if there's an effect between the structural variations and survival, the degree of survival in the environment, then the evolutionary process is underway. And those are the four conditions that are needed, and those are the four conditions which we simulate inside a computer in this genetic algorithm or genetic programming process that I'm going to describe. Now, the notion that Darwin's ideas about natural selections might be useful for solving the problem of machine intelligence occurred to Alan Turing in 1948. Several years, by the way, before Watson and Crick elucidated the structure of DNA, which helps make this whole process a little easier to understand. And Turing observed that whatever machine intelligence or artificial intelligence or machine learning it probably is founded on search, which is more or less an accepted notion in the fields of AI and ML and automated learning. And he said there probably would prove to be three ways of conducting this search. One would be a logic-based search, obviously at the top of his mind, given Gödel's work and his work in enumerating computer programs and the different theoretical papers. Then what he called a cultural search, this is 1948, remember, where we'd rely on knowledge and expertise acquired over the years and somehow apply that. Obviously, he hadn't heard the term expert system or knowledge base or any of the buzzwords of the last 50 years of artificial intelligence, but indeed this cultural search is in fact the knowledge-based search. And then remarkably, he said there would be a third way of conducting the search process to achieve a machine intelligence, and that is what he called the genetical or evolutionary search. And the key phrase in his paper, not just that there'd be a genetic or evolutionary search, which itself was an insight, but a search driven by a combination of genes, not just one gene, not just blue eyes, brown eyes, but complex combinations of multiple factors that are being searched for. And that indeed is the essence of why genetic algorithms and genetic programming work. And he goes on to talk about how this search might be conducted. And he says that the structure of the machine that's going to be reproduced is the hereditary material. Again, not knowing what we now know about DNA. That there would be changes, which he broadly called mutation, and that natural selection would be the process that would drive it. It would be some judgment that would be made of the entities, and that judgment is what we call a fitness measure. So here we are. The reason for talking about genetic programming is that we're trying to address the problem of getting computers to solve problems without programming them explicitly. A goal that has been stated many times by many different people, certainly in the 50s, but also particularly by Art Samuels, one of the leaders and pioneers in machine learning. And the criteria for success in artificial intelligence or machine learning is simply that the machines somehow exhibit behavior that would be supposed to have required a human to have done, sort of a Turing light test for success. So over the years, in the machine learning and artificial intelligence fields, there have been all kinds of representations suggested for pursuing this goal of getting computers to solve problems automatically. Neural nets, horn clauses, Bayesian networks, propositional logic. You can go to the library and look at the last 30 years of the proceedings of the AAAI and ISHCAI, and you'll find a whole variety of different representational techniques that have been proposed. But one that's almost entirely absent in most of that literature disappeared as a tiny subcategory in ISHCAI and AAAI around 1980 is the notion of program synthesis, that is, automatic creation of computer programs. And that's the essence of the idea of genetic programming, which is that this search for the way to get computers to solve problems automatically should not be conducted in the world of logic, should not be conducted in the world of neural nets or Bayesian networks or any of these other things, but it should be conducted in the world of computer programs. That computer programs are the best representation for computer programs, a statement you can view as either platitudinous or insightful or arrogant, as you choose, but that's the foundational thought of genetic programming. And when we talk about programs, we're talking about the sort of thing you all write all the time, and millions of programmers around the world write, entities that have multiple steps with inputs and outputs, and that contain things like subroutines that reuse sequences of code that you've written once, possibly parameterized so that they're reused in slightly different ways, and contain loops that reuse sequences of code that you've written, again, with possibly slightly different data and possibly slightly different substeps, and recursions. And then the other kind of reuse, storage. Computers store the result of executing sequences of instructions. So storage is a fourth kind of reuse. And all four of these kinds of reuse are what give computer programs the leverage to solve very complex problems as opposed to single-stranded problems. So when we talk about programs for purpose of GP, we'd like you to think of them in terms of a parse tree. If you lift the hood under your C compiler, you'll find a parse tree, or your favorite language, COBOL or Fortran, what have you. Thinking of this in terms of Lisp is helpful. That is a functional programming language where there are functions and terminals, and where the programs can be thought of as lists or trees, and where the programs contain functions of 0 or more arguments that operate on the output of yet other functions. And here's a simple program tree or a list that says, if the time is greater than 10, give me a 3, and then add that to 1 and 2 and produce an output. That would be a program tree or a Lisp S expression, Lisp symbolic expression, or a Lisp program. And one of the interesting things about Lisp is that program parts can be executed as executable functions, so that programs and data are more or less equivalent. And that's important because we're going to be manipulating programs, and this is handy to do. Now, this flowchart is not necessarily easy to read off that screen, but let me tell you what it is. It's basically the flowchart for genetic programming, where we start by creating an initial random population of individuals of some sort, some individual computer programs. We execute those programs. We ask the question, how well does the program do at solving your problem? And then we rank the programs based on fitness, that is, how well they did. And then we manipulate the individuals in this population of programs with genetic operators, of which the simplest is reproduction, where we just copy a program. The next simplest is mutation, where we make a slight change in a single program. And the most interesting of which is crossover, where we sexually recombine two computer programs by taking parts of one and parts of another to perform offspring. So let me illustrate the steps of this flowchart a little more specifically. Let's start with the random creation of a population of hundreds or thousands of computer programs. Now, we could do that by going to CS 106 and getting the students' papers. That would give us some random programs. On the other hand, we might do it the way we do it in GP, where we recursively generate the population using a tree growing process, where we reach into the sack of functions, which in this case are addition, subtraction, multiplication, division, and if less than or equal, which you'll note are the functions, the core functions of every general purpose computer since electronic computers started in the 40s, the arithmetic operations and conditionals. So we might reach in and get a plus, which might take two arguments, in which case we reach into the sack again, and maybe we get a times, a multiplication, and maybe the next time we reach into the sack we get a terminal, in which case the growth process would have terminated on that thread, and we similarly complete that process. So that's the step of randomly creating the programs. Now, we don't always start with randomly created programs. What we usually do, you can be smart and put in some programs and seed the population, either slightly or exclusively, with pre-written programs. But normally we start with randomly created programs. Mutation is the simplest of the operators. We start with a program tree like the one you see in the middle there. This is a Boolean program tree with some ands and ors and some Boolean inputs. We pick a point at random, maybe point 2, and then we delete the subtree at point 2, and we regrow a new subtree in its place using the same procedure that we used to create the initial random population. So here we've deleted this subtree and we've grown this new subtree, and that's mutation. And if you started with a population consisting of syntactically valid executable programs, if you perform that operation, you will continue to have that, assuming the function set is closed in the sense that any function can accept as its input the output of any other function, which is normally the case, but again, it doesn't always have to exactly be that way. So now let's talk about crossover, which is the more creative operation. This is an operation that works on two individuals. It's a sexual recombination operator where we pick a subtree at random in one individual. And of course, you'll notice here that these individuals are of different sizes and shape. Well, that's because we randomly generated them in generation 0. So they have different numbers of total points and different topological structure. So maybe we pick this subtree at 2, and maybe we pick this sub-expression over here, and then we do the crossover, which basically involves taking the subtree of one and moving it over as the subtree of the other. And again, if we started out with a population of syntactically valid executable programs, we will end up with that. Well, that's all there is to the genetic algorithm. The flowchart says start with your initial random population, perform these genetic operations, create a new population, execute the programs in that new population of generation 1 or I plus 1, and then rank them again and probabilistically select individuals from the population to either be copied in whole, mutated, or crossed over in pairs. So that would qualify, I think, as what you called a simple idea at the beginning when you were introducing me. So now let's talk about how we go about applying this to a particular problem. And we have what we call preparatory steps. And we're very religious about identifying the preparatory steps because our interest here is to be very clear about what the human user is bringing to this party and what the automated process is producing for the human user. So we want to be very clear what the human is bringing to the party. And the human brings 5 things to the party. The set of functions, so we saw functions a minute ago, plus, minus, times, divide, if. That requires knowledge that those work pretty well as basic functions in computer programs. Set of terminals, which include things such as inputs from the outside world, constants in whatever domain of numbers you're dealing with, say real numbers, floating point numbers, or potentially zero argument functions. And then the fitness measure. The fitness measure is what you want the eventual evolved entity to be good at doing. And then we have parameters. What size population should I use? How many generations should I run this for? Should I do 1% mutation or 3% mutation versus 90% crossover versus 8% of reproduction or whatever? There are some administrative parameters. And then we need to decide when we're going to terminate the run, either through recognizing a satisfactory result or getting tired or running out of computer time, whatever the reason, we need a termination criteria. So let me quickly take you through a run of genetic programming on a totally trivial problem. We're trying to find the computer program that generated this data, the independent data. The input is on the left, the numbers are on the right. I'm going to go through the 5 preparatory steps that we always go through, which is we identify the functions, which are arithmetic in this case, the input, which are the terminals, which is an input and constants, the fitness function, how close does this computer program come to the output in that table when we check 21 inputs. And we add up, say, the sum of the absolute values, which is a very common way of doing that. We pick a population size, which will be 4 for this contrived example, and we will terminate when we get a very tiny error. So let's create our initial random population. Here's 4 program trees. The first one is x plus 1, or represents x plus 1. Second one represents x squared plus 1. Second one adds 2 and 0 to create a constant output of 2. And the third one, or fourth one, produces a straight line x. And what is fitness? Well, that data forms a curve, and the fitness is the black area between the curve, which represents the data over the 21 points between -1 and +1, and the function. So the one on the left, which is the best and most fit individual in the random population, as you can see, has the least black area. The straight line x plus 1 hugs the curve better than any of the other 3 randomly created programs. The worst one is the one on the right that has the largest error. And now we're going to perform the genetic operation. So we're going to select individuals from the population probabilistically based on fitness. So we're not going to take necessarily the best. We're not going to exclude the worst. We're simply going to probabilistically spin a roulette wheel and choose individuals proportional to fitness or by ranked fitness or something like that. So let's say we happen to pick the best individual for reproduction. That's individual number 1 on the left, and we will copy that into generation 1. And then let's say we pick individual number 3, the third best, for a mutation. And we do a mutation by picking point number 2 as the mutation point, and we mutate that individual. And then we do a crossover that takes 2 parents and produces 2 offspring. And we do this as it happens on the first and the second best individual. And one of the offsprings of crossover, when we pick the plus sign from parent A and the leftmost X from parent B, is this rather stunted offspring number C. But the other offspring from the fitness produces this program tree x squared plus x plus 1, which, as it turns out, is an algebraically correct solution to the problem, because we were, in fact, regressing to the polynomial x squared plus x plus 1. So what have we done here? Well, first of all, we've shown you that GP worked. It created a computer program that solved a particular problem, that is, giving a mathematical expression that matches the data. Maybe that data was your value of your credit default swaps that are about to be bailed out. Or maybe it was some scientific data, or maybe you were doing some modeling problem of some sort. So A, it worked. B, the process here determined the size and shape of the solution. We didn't tell GP that the solution was a quadratic polynomial, could have been a higher order polynomial, could have been a rational polynomial, could have been something else. That was discovered through the process. So the size and shape of the solution came about automatically, as did obviously the number of steps and the sequence of steps. And the interesting thing is that the solution, x squared plus x plus 1, resulted directly from a crossover from 2 pretty good individuals in the previous population, namely that linear term x, which was, if you recall, the best fit to the curve among the 4 miserable individuals, and the quadratic term x squared plus 1, which was the second best. So it was that combination of 2 pretty good individuals' characteristics that produced the outcome. So what we have just demonstrated is a probabilistic selection process. We've created a computer program automatically. Let me quickly do it for a second, slightly harder example, where this time in the function set, we didn't quite know what we were doing, so we put in sines and cosines and exponentials, not really very wisely, but we're running this now in a population of 500 individuals for 51 generations using a fairly typical set of parameters: 1% mutation, 9% reproduction, 90% crossover. And the individuals obviously look more complex. We have here this individual, the median from generation 0, is this complicated expression which isn't too good. Here in some later generation, you've got, or the best of generation 0, you've got a little better fit. In an intermediate generation, you're getting towards a polynomial. And then after 34 generations, we come up with this expression, which happens to be equivalent to that quartic polynomial. And the lesson here is, first of all, look at that quartic polynomial versus the arithmetic expression. Obviously, this is a very complicated and overblown way of saying x to the 4th plus x cubed plus x squared plus x. And you certainly would never take the cosine of the difference of x and x to create the constant 1. But this is precisely what evolution does. It works with what it's given, and it produces a result that hopefully works. So, and it's typically not parsimonious, at least if you haven't done any kind of addition to your fitness measure to force it into a parsimonious solution. The interesting thing here is, even though you were inept in putting the sine and the exponential into the function set, and we didn't need those at all, GP quickly got rid of those in most cases, and the exception that proves the rule was the cosine of x minus x. Yes, the cosine function was there, but it was used in a completely degenerate way. And had we run this for a few more generations or in a different run, that wouldn't have been there. But the point of this is, and the reason we call this symbolic regression, is that we're doing regression, but we're doing it in a way that we don't specify in advance the nature of the solution. So you can now go through many of the toy problems from the late 1980s and early 1990s in machine learning and artificial intelligence, wall followers, box movers, truck backer uppers, and whatnot. And in our first book in 1992, we did a Sherman's march through all these toy problems that were rattling around the literature of neural nets and machine learning and AI and what have you, and demonstrated that this one technique could solve all those problems in a unified way. That is, the same algorithm, the same 5 preparatory steps, and no tweaking and fashioning and helping it along. So now I'd like to move on to the somewhat more interesting content, which is the evolution of complex structures, such as circuits and antennas and whatnot. And for that we use what the mathematicians, with their technical terminology, call a trick. And the trick is we don't try to evolve, say, the electrical circuit. We evolve a computer program containing instructions on how to build the circuit. And this is fashioned after developmental biology, where you start with a very simple embryo and a developmental process occurs and a more complex structure evolves. And this is discussed in great detail in our third book, but let me give you a couple of quick examples. Suppose you want to evolve an antenna. Well, instead of evolving the geometry of the antenna, we create something that looks like a computer program where a turtle walks around. So if this is a two-dimensional antenna, the turtle may start pointing north. We may have it turn right by a certain amount of radians. We may then draw a line, and we may then move forward without adding any wire, which is this gap here. We may draw another line. We may move things in a translation, and we may repeat this a few times. So this is a computer program, lines 1 through 8 in Lisp, using functions that allow a turtle to basically create a wire antenna by moving around and dropping metal or not as we instruct it. And from this you can evolve antennas, such as the antenna invented, the Yagi-Yuta antenna invented in the 20s. So let's take another domain, optical lens systems. Up here is a patented lens system from the 1940s. Contains some glass lenses, one nested lens. Lens systems are described with prescriptions, which are basically tables that tell from what distance do you go and what curvature do you put in, what kind of material, what kind of glass do you use, and so forth. And this data structure is in effect equivalent to the optical lens system up there. And it's this data structure we're trying to create. And the way we do this developmentally, again, is with a turtle. In this case, the turtle moves along a line, and at a certain point introduces a curved surface, then introduces a second curved surface and fills it with glass, adds another curved surface, in this case adds a surface with consecutive glass, and we end up with a developmental system for creating a lens system. Let's do this now with electrical circuits, which I want to spend a lot more time on, but I want you to see the similarity of concept here, that we're in each case trying to have a programmatic structure that is amenable to applying this evolutionary process to, and have it describe the ultimate circuit. So here we have a circuit with a voltage source, a source resistor. Z1 and Z0 are wires. They're what we call modifiable wires. So this is the embryo, and the input signal goes through the resistor and around to ground, and the output of this circuit is nothing, a constant 0. This is our embryo. It's a simple circuit that has a place for an input, a place for an output, and we're trying to evolve something from this. That's what we'll call our initial circuit or our embryo. So let me switch now to an animated GIF that shows this developmental process as it would work for a circuit. Let's see. And as you can see here, the modifiable wire has been turned into a capacitor, and now this other modifiable wire is being turned into another modifiable wire with its polarity reversed. And now we just did a series division of the capacitor into two capacitors, and we're about to turn the modifiable wire into a inductor, and now we're going to flip meaninglessly the capacitor around on its polarity. We've divided a wire into thirds. We just changed a capacitor to an inductor, and we just started fooling with the another modifiable wire, and we're about to add a second inductor in series with a different value, the value being set by these subtrees. So what I'm trying to show you here is that we have this bushy program tree that started with the meaninglessly simple embryonic circuit and the execution of the program steps, which inserted capacitors of specified value, inserted inductors of specified value, switched polarities, did series divisions, can do parallel divisions. All of that came about. So here's the Lisp program, here's the program tree, and if we did this step by step, which would be too time consuming, the first thing that happens here is the modifiable wire is being replaced by the capacitor due to this C function, the capacitor inserting function, and the capacitance of the capacitor is set by this arithmetic expression that sets a numerical value. Here was that series division, and so forth. So here's the process by which we develop the circuit from the program tree. Okay? So think of a population now of 100,000 randomly created circuit constructing program trees. We're going to develop each of them into the electrical circuit by impacting the embryonic circuit with the component inserting or topology modifying functions in the program tree. Series divisions are parallel, those are topology modifiers. And we're going to get a fully evolved circuit. We're going to translate that circuit into a net graph, a computer science structure. We're then going to create an ASCII net list, an EE department data structure, suitable for describing an electrical circuit line by line, capacitor of a certain value between nodes 14 and 18, inductor of certain value between 18 and 34, whatever. Then we're going to find out how good each of these 100,000 circuits are at doing whatever it is we want done. So how are we going to do that? Well, we could build 100,000 breadboards and attach an oscilloscope, but since we're in the CS department building, we will use a simulator, SPICE. We will simulate the 100,000 circuits, and then we will look at the circuit's behavior. And SPICE gives you all kinds of behavior, the frequency domain, the poles and zeros, the time domain, and depending on what we want, we'll assign a fitness. So let's say we're trying to design a low-pass filter so that you can enjoy the bass notes out of your hi-fi speaker, your woofer speaker. So what is the fitness function for a low-pass filter? Well, it's in the frequency domain. For low frequencies, say between 10 hertz and 1,000 hertz, we'd like full power to come out. Then we'd like a sharp drop-off. That's the essence of a filter. And at low frequency, ideally no power, at high frequencies. So the fitness function could be the sum over 50 or 100 points taken at logarithmically equal intervals over several decades of frequency, and to the extent it matches this desired performance curve, that would make a good low-pass filter. So what are the preparatory steps? The same as they were for the trivial original problem. We pick the functions, which in this case are circuit building functions. Insert a capacitor, insert an inductor, do a series division, do a parallel division, do a via, in other words, a wire from here to there, run a wire to ground, et cetera, et cetera. So we have a function set. And remember, in this complicated structure, we also have numbers rattling around because that's what determines the values of these capacitors. So we have to have a little arithmetic for the arithmetic performing subtrees. But basically, this is the same old 5 preparatory steps. And the fitness measure is basically very much like the quadratic curve I showed you at the beginning. How well does the performance of the filter match the low-pass filter performance? And if you run this on a population of 1,000 will do fine. On a 15-year-old computer, it'll take about 2 or 3 hours. You will start inventing things that were patented in 1917, in the 1920s, and the 1930s, namely things like the Campbell filter patented by AT&T, whose claim 1 is here, and which this evolved circuit exactly infringes. Or the 1925 Zobel filter, which has a little different substructure here on this part of the ladder, inductor and a capacitor, and has correspondingly a different performance. Or you'll get Butterworth filters or Johnson filters or Cauer or elliptic filters. And if you start changing the fitness function and making it a little more precise, like precise being the sort of characteristics if you took a filter course, and I assume many people in this room at some point in their careers took the classic EE course involving low-pass filters. Each of these filters has some particular advantage in terms of sharpness of drop or this or that or the other thing, attenuation here or there. If you express that in your fitness measure, you will get all these different filters. And in fact, there have been dozens of previously patented inventions from the early part of the 20th century that were churned out with this kind of process. And in fact, post-2000, we went back to the patent literature and picked out some patents that were patented, usually by universities or big companies, after 2000, and we were able to evolve circuits that had the same performance characteristics, and in 5 out of 6 cases did not infringe the original patents, but had all the characteristics specified by the patent, which ought to suggest to you that it is possible to create patentable inventions, not only from the 20s, but the recent last few years, as done by real electrical engineers working on real problems of real difficulty. So that's what we mean when we say this is an invention machine. And indeed, we've created an invention of our own and received a patent of our own on a general purpose controller. Now, if you can evolve things that are as good as humans worked on and invented, and were paid to work on and invent and rewarded to work on and invent, you could, it might occur to you, you might want to invent some things that did the same thing as patentable inventions, but didn't infringe on the patents that were already issued. So suppose you were back there in the 20s and you really didn't want to pay AT&T any royalties for the Campbell filter. And indeed, by the way, many of those other filters I mentioned, the Zobel elliptic filter, the Cauer filter, the Johnson, and the Butterworth filters, were often developed by competitors for precisely that reason. They wanted a filter that did not read on AT&T's patents, or vice versa. So they patented their own. But getting back to that low-pass filter, the basic structure of the Campbell filter, which is the simplest ladder filter there is a ladder So you could create what we call a prior art template and ask, is a given circuit match that template very well? And have a two-part fitness measure. The first part is how well does it do at the job of low-pass filtering, and the second part is how well does it avoid matching too much the ladder structure of the existing patents. And here's two of many compliant filters that popped out. And you can play that game with any number of things. And we accidentally played that game when we did our 6 post-2000 patented inventions, because we didn't tell GP to avoid the existing patents. We just gave GP the specs that the patented invention performed. In 5 out of 6 cases, we got things that in many cases had the exact essence of the invention, but when you read the patent and read the actual words they had used, it didn't infringe. Because usually people who write patents, they're sort of preoccupied with their own way of thinking, and they overload their patent claims with their personal biases, often cluttering up the essence of the invention with extra words that let other people engineer around them. Okay? So a lot of this is described in our 4th book, cleverly called Genetic Programming 4. And many of the examples in that book are what we call human competitive. And when we talk about human competitive, we like to be, again, very methodical and precise. This is not just nice or looks good or came out of our department or company and therefore must be good. We like to create some arm's length measurement of human competitiveness. So these include things like, well, number 2, the result was patented as an invention in the past and is improvement over a patented invention or would qualify today as a patentable new invention. That's one of our 8 criteria for human competitiveness. Or the result is publishable on its own right as a scientific result, not as a result produced by AI or ML for some toy problem that the AI and ML community think is nifty, but a scientific result that is acceptable for publication in the domain itself, irrespective of the fact that it was mechanically created. And we have several others. And there's a parade of these things done by a large number of people now. One of them is Lee Spector, who's the current editor of the Genetic Programming and Evolvable Hardware Journal. He has evolved numerous quantum computer circuits which were better than those in the physics literature or the literature of that field. There have been some game players. There have been some transmembrane segment identification algorithms, which there's 43 in the literature, but this particular one is slightly better than all of them. Sorting networks, obviously some low-pass filters of the type we've already mentioned, all kinds of electrical circuits for time-optimal control of robots, electronic thermometers made up only of transistors and resistors that, using the quirks of the components, actually measure the temperature. Voltage reference circuits, a famous major invention in the EE field. Cellular automata rules, protein motif identifiers. We've rediscovered the PID controller. We created a circuit, the Philbrick circuit. Did some layout things. Did the PID squared controller, and other people have done all kinds of other things. This is a PID controller we call a parameterized topology. Not only evolved the topology of the controller with leads and lags and adders and subtractors and gain elements, but there are equations that give the parameter values of these leads and lags, and the equations have been evolved so that this controller satisfies a category of problems with a given free variable. And that's what we call And Jason Lahn over at NASA developed this antenna, which went up on one of the satellites and is actually being used. There's an annual competition called the UMIs, where you can read all kinds of interesting things that other people have done in a number of different fields. So the point I'm trying to convey here is that, first of all, we've produced human competitive, we and other people in this field have produced human competitive entities of various types in various domains. We've done it with the same basic, simple flowchart that I showed you right at the beginning, that all of these problems are approached with the same 5 preparatory steps. We haven't had a new idea in 15 or 20 years. And this is a unified method for automatically creating computer programs, or more pertinently to the title of my talk today, a automated method for designing complex structures from all these different domains. And getting back to AI and the Turing test, or the Turing light test as I like to call it, these results have what we call a high AI ratio. That is, artificial to intelligence ratio. The automated method, that is genetic programming, has delivered a lot in relation to the amount of intelligence introduced for that specific problem by the user. So when we went from filters to amplifiers, what we did is we changed the fitness measure. We went from matching that standard brick wall frequency domain performance curve to a fitness measure that primarily considered gain, but also distortion and bias, and then later on power supply rejection ratio and parts count, and you can include power usage or cost of the components, all sorts of things that you like. So that's the high return based on a good AI ratio. And the other key point is this is what we call routine. That is, we consider a problem-solving method like GP routine if relatively little human effort is required to get the method to handle new problems in the same domain or to move from domain to domain. Now, what do I mean by that? Well, you may think it's important that Darwin's 200th anniversary was within the week, but this same day happens to be the 13th anniversary of the first talk I gave at EE 380 in 1996, and we had just produced our first circuit with a transistor, which was this powerful 10 decibel amplifier that you see here, which turns out to be a rather ludicrous circuit, but it does what it was supposed to do. It gave 10 dB of amplification. And the point was, we had previously done those low-pass filters, the Campbell filter and the simple ones, which only involved linear components, resistors, capacitors, inductors. Then we said, let's do active circuits. So we went from the first half of the 20th century to the middle of the 20th century when transistors came in. What did we change in our computer code to move from inactive linear circuits to nonlinear active circuits? The answer was we added one function to the function set, which was a transistor inserting function, which took a wire and broke it and inserted a transistor. That was what we did. So that's what we call routine, because we were able to move between two major domains of electrical engineering with an absolutely inconsequential and trivial change in the structure of genetic programming. So let me race ahead and now talk about what have we learned since that first lecture. Well, first of all, lots of other people have helped us learn a lot of other things and have worked on these different other areas. But now enough different human competitive results have been produced that we can look over these multiple areas of antennas and quantum computing circuits and analog circuits and laid out, we can do layout too, by the way, laid out electrical circuits, controllers, mechanical systems, and say what are some of the lessons we can observe And remember now we're talking about work that in many cases have been done by other people with their own code, in their own labs, with their own computer, and their own way of looking at it, and yet we find some interesting similarities. One, and this is really, really interesting, you don't have to be very smart to use this. What we say is native representations are usually sufficient. What do we mean by native representation? Well, we mean that net list that everybody in EE knows is a description of a circuit, or that geometry table, which is the exact description of an antenna in 2 or 3 dimensions, or the prescription, the thing you see here, which is this data structure table that describes lens systems. There would be nothing wrong with being clever and coming up with really complicated representations, but the interesting thing is all of the people, us and these other groups that have worked on it around the world, have started with native representations and rarely leave native representations. So the point is you can work with what's already working in whatever field you want to conduct your design in. Another observation, GP starts small. Well, it means that the best circuit in 100,000 initial population of optical lens systems is very likely to be a very simple lens system, maybe with one piece of glass. Or it might be a simple single ladder in what may ultimately become a multi-ladder circuit. Or it may be only a few leads and lags in what may become a bigger controller, or maybe just a few wires in what may become a complicated antenna. Now, why is that? Well, at generation 0, you're working with randomly created programs. So if you start having too much structure, the chance that you will have randomly picked the exact right way of connecting 2 or 3 or 4 or 5 electrical components and assigning meaningful values to them and getting plausible results is tiny. So GP, I think we can confidently say does start small and probably will always start small. We often use simulators, not always. Sometimes we go to the real world and we've attached a PC to a field programmable gate array and manipulated the bits that change the gates 1,000 times a second and run some inputs through the gate array, and then this is a reconfigurable gate array, and then do that again 1,000 times a second. But usually we're talking about simulators. Of course, there's reconfigurable antennas. There are people who've done lab bench work with lasers where they've flashed the laser at something and done measurements and put the laser measurements inside the inner loop of genetic programming to actually report the real-world physical numbers. But generally, we're talking about simulators. And the interesting thing about this simulation, shown by this botched figure here, is that as you go from generation to generation, at generation 0, which is over here, the percent of unsimulatable individuals, it might be 90, 95, 98%, but very quickly it goes down. Now, I can't give you any reason why that has to be, but it has been observed over and over again that GP gives you on a silver platter simulatability as you proceed through the generations. So if you just get something out of generation 0, you will move along probably nicely. It engineers around existing patents because normally it doesn't know the patents are there unless you're explicitly adding that to your fitness measure. There are many ways to solve a problem. The way that was patented is not always or likely to be the only possible way, maybe the only way that a smart human may think of because his head is cluttered up with too much knowledge, but GP doesn't have that problem. Now the clock is either lying or I'm running behind, so let me quickly cover, just by mentioning, we can do things like subroutines, can involve memory of all types, matrix memory, relational memory, queues, lists, what have you. We can do automatically defined iterations where iterations are inserted into computer programs. Don't have time to explain this. You can read all 4 of my books to get up to date on this. We can do recursions and loops, and we can even evolve the architecture of programs with what we call architecture-altering operations, which are patterned after gene duplication. Again, all to be left as an exercise to the student to read. Interestingly, you can evolve complex. This is a tree describing a circuit. Here's the circuit. Those little boxes in the circuit are actually not only subroutines of reusable subcomponents, but they are subroutines into which we have passed a parameter. So you can do all the different things that you love to do when you write computer programs with loops, recursions, and memory. Somebody somewhere has probably already done this with GP and written a paper about it and flown off to a conference and presented it. This is the example of the code that describes that circuit you just saw. And we can do these parameterized topologies, which are actually general purpose solutions to a problem. So this is a variable cutoff low-pass filter. You'll notice that there's a circuit here with components, but each component has an equation attached to it. Those equations were evolved automatically, and they are equations that contain a free variable, such as the cutoff frequency, and they give the values of the components. So all kinds of things can be done. As I mentioned at the beginning, computer power is the key to this thing. We are talking about big populations, although they're not so big today. We just carted away our 1,000-node computer to the junk heap. Nobody would pay anything for it. It was 9 years old, and it suffered financial death due to Moore's law. But lots of computer power is important. And the nice thing about genetic algorithms and GP is you can easily parallelize this code in many different ways. The most trivial way is a master-slave situation where one computer simply parcels out these fitness evaluations, which incidentally I would use up all the computer time. It's not the genetic operations. Or you can do an island model where you have subpopulations in semi-isolated subpopulations. So there's a small amount of immigration between the subpopulations from New Zealand to Australia. Same thing that gives rise to speciation if you read Darwin's other book. And the island model works very well. And Moore's law, our particular group over a number of year period has had 5 different computers that we've used, starting with a Lisp machine, which maybe somebody in this room remembers. I see some nods. You remember how fast they were. And that was used to produce most of the toy problems that were in our first book. Then we got a 64-node transputer network with convenient 1-byte arithmetic and all sorts of other handy features. Later we got a real 64-node computer with a real chip at each node. And we started increasing the number of human competitive results. By coincidence, as we look back over these 5 computers over time, we actually had about a 10-to-1 increase in computer power with each of those phases. And if you match those phases up with the results in the 4 books, what you find is 5 different categories. The Lisp machine with its toy problems, the first human competitive results, but not as good as a patented invention, but human competitive in the sense that it was better than some algorithm that was published in some paper by somebody who was interested in the subject, which we usually weren't, but that was the second category with the second computer. 20th century patented inventions, most of the RLC circuits and the simple controllers and the very simplest transistor circuits fit in that category. Then another 10-fold increase in computer power gave us those 21st century patented inventions. And then our patentable new invention, the one we got the patent on, the general purpose controller, which was a long time, our biggest eater of computer time. Our typical run is 1 to 3 days on 1,000 nodes in phase 4. For this patentable new invention that we got, it was a 30-day run on a 1,000 node computer. Fortunately, it worked the first time. And that was another 10 to 1 increase. So we had this layer cake corresponding to the different computer systems and the Moore's law cycle working relentlessly every couple of years, allowing us to ride the surf wave of Moore's law. And what that means is every 10 years there's a 100-fold increase in computer power for the same alleged economic cost. So as we go forward, we're saying right now many different groups have invented things that were previously patentable, in some cases gotten them new patents. So it's human competitive now. In 10 years, there'll be 100 times more computer power available to those same kinds of researchers with their same kinds of budget. That ought to produce a huge step up in the complexity of that which can be invented. And we think the next layer of this layer cake are commercially usable, patentable new inventions. And that's what we're hypothesizing will be the next step. Now, I could go through all these different things about what are promising areas, but maybe I should allow a few minutes for questions. So let me just mention there's some pithy advice on what kind of problems these are good at solving. Basically are those ones that you don't understand very well and that human engineers don't understand very well, and that's a black art. If it's a black art, GP is a good thing to use. And there's lots of books on GP. There's 4 different annual conferences, edited books, book series, 20-some books, 5,000 papers, 1,000 authors, mailing lists, websites, etc., all of which are in the documentation. So thank you very much.
We have a few minutes. One thing that struck me about the randomness is that in the crossover you didn't choose sort of related individuals and exchange related parts, whereas we know that sort of in the wild evolution that somewhat related entities end up doing crossovers, or at least geographically related.
Well, we're assuming, I think, that these are all the same species, but the structure here is more complex than my hand-waving 50-minute lecture may have suggested. For example, when you have that program tree for a circuit, there's a syntactic structure to that.
Yeah.
So, for example, if you have a capacitor inserting function here, there's a subtree that contains numbers or arithmetic or even free variables that determine the value of that capacitor. So when you do the crossover, you don't mingle the subtree, the value setting subtree for a component. You don't cross that over with, say, a series or parallel divide. So there's a syntactic structure. It's a syntax preserving crossover in practice. It was not so with that simple first example with the quadratic equation. There was no syntactic structure. It was simply had an unrestricted set of functions and terminals that could be glommed together any way you want. But in practice, you're absolutely right. It's not as undefined as I may have suggested.
What's the trade-off between the time for evolving a useful device and involving, say, in your antenna example, an antenna expert at your choosing of the functional blocks and rules for the crossing over the two populations?
I'm not sure I caught the essence of that.
So to evolve to a useful antenna, say,
right,
it takes a certain amount of time, and you're starting from a very, very basic set of elements or basic embryo. If you involved an antenna designer, somebody with expertise in antenna designs at the beginning, have you observed that decreases the amount of cycles through the evolutionary need? If you have an expert choose the functions.
Well, the functions and terminals don't change that much. So, for example, for antennas, the only thing that's in the function set, if it's a two-dimensional antenna, is that a turtle is moving around, if it's a wire antenna, and dropping wire. If it's 3D, that's a flying turtle, and it's spinning wire. And if it's a contoured antenna, in other words, the functions and terminals are simply a very simple and minimal set of functions that are sufficient to describe the geometry table for antennas, or the net list for circuits, or the geometry of a controller, or the prescription for a lens system. We don't need an expert to tell us that capacitors and transistors, for example, make up, and resistors, are the components in modern-day electrical circuits. That was the amount of expertise we needed, is that those are the components to put in. We didn't put in timers or other things. We put in things, but there's very little expertise involved in choosing the function set. And usually those same functions work for a vast variety of different antennas or circuits.
You said you jumped your 1,000-node Pentium 2 system. What is sort of the equivalent system you would put together today with the same horsepower?
Oh, well, we haven't. We're in the process of doing that. And I might add, if anyone is really interested in this, some of you are PhD students and are interested in working on a thesis in this area, and as I say, we're potentially trolling around to produce commercially usable inventions. So if you're older than a student status and really interested in this, you might contact us. But at the moment, we have no immediate replacement. We will probably use a cloud computer in the near term.
But as you're thinking that a typical core, you get quad-core processors these days. So as you're thinking that a typical core is the equivalent to like 10 P2s? Or a reasonable multiple?
We called our 1,000-node computer, it was big in 1999, but then we called it the incredible shrinking computer, because had we bought, for instance, standalone Pentiums, single-core Pentiums today, we could, roughly 50 nodes would have done the same amount of computation as the 1,000. And of course, as you correctly point out, now you can get the multiple core things, which GP can use. It may be tough to make your spreadsheet effectively use an 8-core or a 4-core computer, but we have no problem using every last drop of computer power that's hiding in every one of those chips, because this parallelization process is extremely efficient. Okay, it's not like normal parallelization where you're taking things that were never intended to be parallelized and shoehorning them into a parallel architecture and getting 10% efficiency. We run up there in the high 90s. There's, like with that island model, there's very little wastage. We use everything in the pig, including the oink.
That suggests that you should subvert the SETI at home people, because they get tens of thousands.
Well, that's an excellent suggestion. If there was some altruistic reason why people would like to help
the SETI guy didn't show up today.
Design things, that is another option of the more informal type of cloud. That's a very viable way to do this.
We just have to come up with a problem that somebody would say, okay, yeah, instead of finding Martians, I'm going to find, I don't know, my classic is cure to cancer.
Well, if we could characterize something as a cure to cancer, you could probably get the kind of altruistic participation if it's, Intel devising a some circuit, I don't think anyone's going to go out of their way to, maybe with micropayments to people with idle computers at home, that will change. There's all kinds of ways to skin a cat here.
Yeah.
Well, thank you very much. And, oh, sorry, one last.
Have you played yet with this newly discovered component called the memristor?
Interesting that you ask. We have been reading about that avidly. Fascinating that you asked.
For more, please visit us at stanford.edu.